Hi guys. I'll just wait for a minute. Did you all get the homework assignment, the take-home exam? Yeah, so it shouldn't be too difficult if you've been coming to class. And I guess for the final, I said I'll do something similar. If any students wanted to write a term paper instead of a final exam, then if you get in contact, we can talk about that. So there will be a take-home final that will have the same structure. If any of you wanted to just focus on one thing and write a longer paper, then that's an option you can do instead. Okay, so I'm going to talk about Gibson today. And in the past, when I've taught Gibson, I've used his last book, which is called The Ecological Approach to Visual Perception. And I think it's I think it's a really great book, and I really like it. It starts off very slow, it's very detailed. He starts off just with a very detailed step-by-step description of the environment, of the notion of the environment. He talks about how organisms necessarily have an environment. Yeah, and then he talks about what our environment is like. It's a sort of cluttered environment in which you basically have surfaces arranged in a certain way. So you've got this environment that contains many surfaces. And then he thinks that an environment for an organism offers possibilities of action. So this is something that isn't so clear in the short thing I sent you. Yeah, that an environment, one way of thinking about an environment is what an environment is just a very complex set of connected action possibilities. Yeah, there are all sorts of things one could do in the environment. And then the function of the visual system, and he calls these possibilities of action affordances. Yeah, so the affordances of an environment are the sort of various possibilities of action that the environment offers you. Yeah, and then the sort of story is that the visual system has evolved to pick up on these possibilities of action. Yeah, that's the sort of big picture. So, and he thinks that the way the visual system does this isn't through some sort of computational processing account, but that there is information within the light that contains information that allows one to there's information in the light on a path through the environment that specifies what sorts of possibilities of action there are going to be in the environment. Yeah. Now, in particular, that think of an environment, there's going to be a bunch of surfaces. And let's think of the most simple environment we can have for a kind of young creature, a flat tabletop. Yeah, so think of a tabletop as a very simple environment. This basically, the main thing you've got is the ground. So one thing about Gibson is that he thinks that the most important surface for us creatures, for creatures who get about through walking, yeah, the most important surface in the environment is the ground. Yeah, so fishes and birds are going to be a bit different. We're going to understand them differently. But for well, birds as well. But for us, we got the ground. And so one really important thing is to know when the ground stops. Like, so one thing that you want to know is you want to know when does the ground stop. And when the ground stops in a major way, you have things like cliff edges. Now, so a cliff edge is going to be a very important type of. So whenever you've got a bunch of surfaces, you've got edges. Yeah. And one of the more important types of edges that the visual system has evolved to detect in land-based creatures are things like cliff edges. Now, how do we, if we're wandering through the environment, how do we avoid falling off cliff edges? That's the first type of edge. Yep. Gibson calls these falling off points. Yeah, so falling off points are really important to be able to spot. Now, it's going to turn out that there's different types of kind of these sort of falling off points. Some of them are dangerous cliff edges. Depending on the size of our legs, some of these edges are going to be steps. Yep. Sometimes we're going to come to a step and it's a sort of like an obstacle. It's too high to climb over. Yeah. So let's suppose we've got a very simple environment, which is just a tabletop. Then all you've got is the only surfaces that you need to worry about are the ground and then the falling off points. Yeah. But then think of a more complex environment. So let's stick a bunch of cubes on the environment. Yep. So you've got a tabletop with a bunch of cubes on. Then the sort of important possibilities of action are going to be what sort of possibilities of passage are there. Yeah. So the animal is going to have to find a sort of pathway through the environment. And once again, that you've got a cliff edge, which is one type of edge, but you've also got, let's think of a doorway. Yeah, you've also got the door. You've got the doorway. You've got wall, and then you've got empty space. So like a doorway and a cliff edge, in some sense, are quite similar. They're what Gibson calls occluding edges. Yeah. So an occluding edge is an edge that has another surface behind it. Yep. And with an occluding edge, like a doorway or a cliff edge, as I move relative to the edge, so as I move relative to the edge of the cliff, or as I move relatively to the door, yep, more and more of the surface behind comes into view. So I'm looking at the door here. I can just see a little bit of the hallway. As I move over, more and more of the hallway is going to come into view. And what it's going to be like is you're going to have an edge here in the visual field as you move. You're going to have an edge here, and then as I move and as I get closer, more and more surface is going to sort of accelerate in. Yeah, so one could take a couple of points as one sees them, then as one moves, you'll see they sort of move away. So at the moment, I mean, this would be easier to do in a three-dimensional space. Yeah, but as I change perspective, the hallway comes into view. Yeah. Now, Gibson thinks that in terms of learning how to perceive our environment, that if what the environment is a bunch of surfaces, this is I think, yep, and what we want to find out are kind of things like, is this a falling off edge? Is this an opening? Is this a passageway? Yep. Then Gibson thinks that we can learn to pick up on these features of these distal features of the environment through information that's contained in the light through possible paths through the light. Yeah. So Gibson in this article we've got, he's trying to explain this aspect of his theory. And so one of the things he sets up is that there are two senses of information. There's a sense of information we get in kind of computer science and in computational models, where information is something that is processed. Information as it's understood in computational accounts is something like a message. Yeah, we're being sent messages. The information is in the retina, and then it gets processed. Yeah, and so information is something that's transferred. Information is something that is processed. These are the sort of metaphors you'll talk about when you talk about information from the computational approach. Who read the Gibson? Yeah, well, how does Gibson contrast this? Gibson says that he understands information. Hasson?
Can you hear me?
Yeah.
Okay. So I think he contrasts with like physical optics and ecological optics, and says that like ecological optics treats the information that is in the it's not a information that we construct based on the retinal image, but like it's an information we get directly from the environment. I think.
Yeah. So I take it. Yeah, Gibson is working on a notion of information. The information is out there in the environment. Now, the information is out there in the light. And I take it one reason he wants to stress this is that our visual systems have evolved in order to pick up on this information. Yep. So he wants a notion of information that can play a role in sort of explaining how evolution works. There's information out there, which is sort of out there regardless of whether or not there's any sort of creature to pick it up. And animals that have vision have evolved in such a way so as to be able to pick up useful information contained in the light. Yeah. And so Gibson introduces Hasson. Yeah, it's a bit noisy there, so I'm gonna mute you just to get rid of your background noise. Yeah. But Gibson thinks that he's got a notion of information where information is not understood in terms of information processing, but there's certain information out there in the light. Now let's have a look at what he has to say. So one thing is who's actually read Gibson before? I just want to get some idea of how much background. I know Hasson has read it in Uzzi's class. Has anyone else read Gibson before? I mean, who's a Gibson virgin? Is it most people? I mean, if most people have read Gibson before, I can go a bit quicker. But if most people haven't read any Gibson, then I'll have to. Okay, so I guess most people haven't read Gibson. Okay. Okay, so in this short paper I gave you, he's trying to summarize some of the ideas in his position. This was written a little bit before the kind of final book, and he says that yeah, so the theory distinguishes between stimulation by light and the information in the light. So and he's interested in offering account not about how we process information, not what's going on internally when we perceive things, but he's primarily interested in the information that's out there, that's available for the visual system to use. And he thinks in some sense this is the big task to work out, in psychology, is to offer an account of what precisely is the information we're using when we're solving certain tasks. There are certain tasks we engage in, such as finding a path through the environment, not falling off cliff edges. And the first question is what exact information are we picking up on in the environment in order to successfully achieve these tasks? And he thinks that we have that sort of the traditional theories of vision get it the wrong way around. They start off by looking at what's on the retina and how this is then processed, rather than thinking about the information out there. So he starts talking about the notion of the term information, and he says there are currently two radically different uses of the word information in psychology. One I will call afferent input information. So this is like this notion of information that we find in computational accounts of perception and various other things, where the information is the input available to the system. And this input somehow carries information about the environment. The other is optic array information. Yeah. The former is familiar. It is the information conceived as impulses in the fibers of the optic nerves. Yeah. According to this computational account, information is assumed to consist of signals to be transmitted from receptors to the brain. And then perception is a process that is supposed to occur in the brain, and the only information for perception must therefore consist of neural inputs to the brain. So that's one notion of information. He's writing this before Ma. Yeah, so I think he'd probably say this slightly differently if he was writing post Ma. Optic array information is something entirely different. Yeah, so the type of, when Gibson's talking about information, he's not talking about something that's processed. Yeah, for Gibson, information is something objective out there in the environment. Yeah, so information in Gibson's sense is observer independent stuff in the environment, and it's stuff in the environment that plays an essential role in explaining how evolution occurred. So our visual systems have evolved the way they have to be able to pick up on this sort of information. Optic array information is something quite entirely different. It is information in light, not in the nervous impulses. It involves geometric projection to a point of observation. So we have this notion of geometric projection to a point of information, not transmission between a sender and receiver. It is outside the observer and available to him, not inside my head. Yeah. The information does not consist of signals to be interpreted, but of structural invariants which need only to be attended to. Elsewhere, he talks about what's important is picking up on this information. So we have the visual system has evolved to be able to pick up on this information. And this information is out there in the light, and we've got certain types of structural invariants out there in the light. Now, what are we to make of this? Well, I'm going to look at a couple of other things he says in this article, and then I'm going to show you some pictures and some videos and try and explain it. So one thing is that normally when we do optics, we have the idea of the sun as a source of light. We say the sun hits a surface, yeah, and then it's reflected onto the retina, and it's focused onto the back of the retina. Gibson thinks, though, that when it comes to vision, what we should be thinking about is the ambient light. So light comes from the sun, it bounces around, and the whole environment we live in, when there's some source of lighting, is structured by, is full of structured light. Yeah, and he calls this ambient light. Yeah, and he says when you've got some ambient light, he says when you're at every point in the medium, is the air, is empty space in some sense. At every point in the medium, there is ambient light. And secondly, the ambient light at every such point will be structured by the reflecting surfaces facing that point. Yeah? So this is at any point in the empty space in a lighted environment, any possible point of information is going to be full of structured light. Now, what exactly does this mean? So let's have a look at his other book. Yeah, so I really like Gibson, and I think Gibson, there's a lot going on in Gibson, and I'm not sure how much of this is going to be obvious and how much is difficult. And the fact that none of you have got your videos on means I've got no idea this is making any sense to you. So do tell me to slow down or to speed up or to just stop and give up. But this is a picture from his book, The Ecological Approach. So this is a, can you see the picture? Can you see my cursor? So here's a potential point of observation. Yeah. Yep. And from this point of observation, we can think of this point as made up of sort of as the sort of apex of nested pyramids. This is a kind of two-dimensional cross-section through a sort of three-dimensional space. And so like here we've got, I don't know, a ball on the ceiling. It's a 1970s, probably the wallpaper is orange. I don't know, but we've got these sort of, we've got this thing here, and maybe there's different textures, so all of this can be subdivided. We've then got this, which is the light coming from the ceiling. We've got this then, the light coming from the wall above the window. Here we've got light coming from the sky. Here we've got light going to the tree, and the tree is going to be made up of leaves. So the kind of, this is pyramids within pyramids. So if for each leaf, we can draw these lines, yeah? Here, there's the wall. Here, there's a table, yeah? So any particular point, you can do a projection from the point to all the surfaces, yeah? And the light is going to be structured in that way, yeah? So that's what a sort of static point of observation is. As you move, though, from one, and everything, all these surfaces are going to be textured. Now, if we're thinking in terms of pixels, I think the way that computers pick up on optic array information is in terms of pixels. But as we move our points of observation from one potential point of observation to another, the way in which the light is structured is going to change. But it's not going to change only. It's going to change in such a way that depends upon the layout of the environment. Yeah. So let's think about potentially moving from one point to another. Yeah. So if we move from this point to this point, yeah, the person, I mean, we can get rid of the observer because this is the information objectively in these points that can then be utilized by an observer. Yeah. But as one moves from this point to this point, as one stands up, the structure in the ambient light changes in a systematic way, in a way that depends upon the layout of the external divisor. And Gibson's most interested in what he's going to call occluding edges. So in particular, I think this edge here, the window, and this edge here, as we stand up, as we move from here to here, suddenly all of this stuff is going to come into view. And if one moves from here to here, let's suppose this is brown and the floor is white. Yep. And say this is yellow. As one stands up, suddenly a whole bunch of white is going to become rushing into the visual field. There's going to be this at this edge. Yep. Suddenly you're going to start seeing the floor. As one moves from here to here, more of this tree is going to come into view. Yeah. Now, as one moves, yeah. Now, so oops. Yeah. So as one moves, you know, when there's an occluding edge, like a cliff edge or a step, suddenly you're going to have stuff coming into view. Yeah. And sorry. And the way things change as one moves basically tells you about there's a lot of information there about the environment, about what sort of edges are occluding edges, and also about the observer's relationship to the environment. Sorry, so I'm just, yeah, oops. So, yeah, so Gibson started working on perception during the Second World War, and he was being trained. He was hired by the Air Force to basically do tests, visual tests on who would be a good pilot. Yeah, and you know, before this, when they tested pilots' vision, they basically sat them down on a chair and made them look at a wall and did the kind of usual visual tests, like how many letters can you read? And it turned out that this sort of information wasn't particularly useful in terms of testing how good someone's vision was to be a pilot. So Gibson was sort of interested in the vision. Gibson started his work looking at the kind of the sort of what's involved in landing an aeroplane, for example. Yeah? What sort of visual cues are there? And so here's a picture. If you're coming down to a runway, yeah, you've got this, as you're coming down to land, you've got this texture coming at you, yeah, as if it's from the point to which you're heading. So if you're in this thing, if the change is input is happening in this way, the way that these sort of arrows represent, then this tells you that you're heading towards this point. Similarly, in terms of knowing if you're about to hit something, if you're aiming at this point, you're coming down, this is the point of impact, that the optical flow is going to be coming out from this point. Yeah. Now I'm not sure how understandable that is, but I've got, oh, hold on. Now, today, the optical flow stuff is quite big in computer engineering, in engineering, and people use optical flow information in for example, training drones, in terms of training self-driving cars about how to avoid obstacles and the like. So today, when it comes to optical flow, I'm going to show you a video. Yeah, so here's an optical flow video. So we're going to watch a video, and what they've done is that the green lines represent optical flow. Yeah, so there's not much. Okay, let's. Yeah, and how this optical flow is calculated is you take one picture and after another one, and then you sort of calculate how much change there is between certain pixels in the first picture and in the second. Yeah, and there's various methods of doing it. Now, like for example, here you've got a bunch of obstacles. Yeah, and when you've got one thing coming from behind another, yep, you get quite a strong sort of vector like this. So having these sort of strong vectors shows that you've got an occluding edge, that you've got some object with another object behind it. Yeah, so yeah, so like you can see like these sort of things here sort of specify the edges of things. I'm going to see if we can. Yep. You also from the information contained in this flow, if you were just showed these flow vectors, you could work out where there were objects to be avoided, and you could also know the direction in which the thing is traveling. Yeah. So abstracting these sort of flow vectors, these optical flow vectors from a sort of series of points of observation contains information not just about the environment, but also about the relationship between the observer and the environment. Yeah, so you know, yeah, so you can see here that as the observer is turning, yeah, we have everything is flowing in this direction. And that's sort of giving you information that the observer is turning. I feel like as no one's there, am I just talking into the void? Is this making any sense? Does anyone have any questions? I mean, I understand this stuff, I think, yeah, but I'm not sure how well I'm sort of making it understandable to you guys. So did any of that make sense? Any sort of...
I have a question, actually.
Yeah, you had a question?
Can you hear me?
Yeah.
I don't know in which earphone the microphone is, so I
Okay.
don't know. My question is like, Gibson thinks that the information is in the environment, like information regarding the three-dimensional structure of an object is in the environment, right? So like they are picking up on the information and they're kind of having these direct representations of objects, let's say. So, but like also this information can also only be gained through navigation in the environment. Like it cannot be gained in a single spot. Like you cannot understand the three-dimensional structure of an object in a single point of observation, right? So like, I mean, like this means that like, an information regarding these can only be gained like in time. It cannot happen in a single moment, but it can happen through time. So like then how can we explain that like any information in light, like if an information in light, it should be in one of these lights, right? It should be like singular or multiple, but like how can lights that are pretend that through time can form a single information? I don't know if I could explain myself, but
yeah,
yeah.
So Gibson thinks that in psychology, when you do psychology experiments, we focus on people having a static, they look at something, they don't move. There's all this emphasis on keeping the head still and just... Gibson thinks that the vision evolved to guide the action of an animal moving through the environment. Yeah, so naturally, in terms of understanding the visual system, that the kind of primary basic way the visual system works involves movement through an environment. Yep. Having said that some animals are able to perceive images, and so Gibson then at the end of his discussion then has a sort of a discussion of our perception of images. Yeah, that is and I take it the reason why movement is important is that as we move from one point of observation to another, basically what's being picked up on are things that are going to be best represented by vectors. Yeah, so when you've got a movement, that this kind of the way these mathematicians, the video I was showing you, is you've basically taken a pair of images and you've translated that pair of images into a bunch of vectors. Yeah, so you compare one static image with another, and then you have these vectors that kind of capture the sort of change that's happened from one to another. And these two different images these two different images can be thought of as static representations of two different positions in the environment. Yeah. Let's assume that nothing else is moving, because perceiving moving objects, that's going to involve another level of complexity. Now, of course, so one thing is that we're kind of constantly moving. Like whenever there's any ambiguity, we can just shift our head slightly. And in terms of, yeah. Now, I mean, my sort of take is that as human beings, we've evolved also to be able to perceive statically. Yeah. I take it one thing that kind of, I mean, if you want to know the layout of the environment, the best way of discovering that is to move. Yeah, so if you want to work out whether there's a path or whether there's is that a cliff edge or is that just a step, you move a little and that gives you the information you need. Like, if you want to know if there's a predator nearby, then maybe the best strategy is to be totally still so that any motion is independent of you. Yeah, so sometimes I think animals stay still in order to be able to kind of observe the movement of a predator. Now, Gibson thinks that so he's got this idea of the environment. What the environment is a set of surfaces. Yeah, and surfaces are joined by edges. And then what we're picking up on this Gibsonian account are particular important types of edges. Yeah, so what this Gibsonian account of perception gives you is an account of how we understand layout. Now, you might think, yeah, I mean, there's nothing in this account, for example, about color. Now, Gibson did say some stuff about color perception, but it's not obviously built into it. That he doesn't say that much about, say, recognition and categorization. Yeah, about how, yeah, so you might think, well, this Gibsonian stuff. So my sort of take is this Gibsonian stuff offers a very nice account about how we are able to, in some sense, understand the basic three-dimensional layout of the environment. Yeah, things like recognizing forms. Yeah, recognizing, oh, it's Hasson again. That might involve something quite different. Yeah, so kind of facial recognition stuff. You might think, well, facial recognition is something that probably evolved a lot later than the basic visual systems. Yeah, and you might be wanting to tell a very different type of story about how facial recognition works. Yeah, there I think you might think that some sort of computational accounts there might be useful. But I think yeah. So I think what this account gives us though is a capacity to kind of directly perceive the basic layout of the environment, where the layout of the environment are a rough kind of grasp of the kind of rough three-dimensional layout of the external environment. So we've got, and most importantly, we've got this kind of surface, the floor, moving away from us. And then we've got kind of objects, we've got doorways, we've got rocks, we've got passageways. I think for that sort of stuff, I think Gibson can give a quite nice account. Now, can you then build up on that to give you a plausible account of, say, object recognition? And I think that Gibson thinks yes. I think that if you want to get from the Gibsonian stuff to object recognition, then I think perhaps the way to go is a sort of vaguely Piagetian one. Yeah, so Piaget kind of offers this account of the development of object permanence. So I think that and the capacity to recognize object permanence, which involves also picking up on what we might think of as higher order, what's it called? Yeah, so I think Gibson himself doesn't offer a worked out account of object perception. He says he gives some hints, but I think yeah. Hesna, you've had your hand up for a while.
Yeah, I was also thinking of a question that's maybe related in some way. So Gibson supports the idea that the information we need is out there in the environment, etc. But this information is somehow vague. You know, for all the organisms maybe need that information and it's there, but our the particular information that is relative to each organism or personal information, etc., is somehow needs processing. And so if even if we do not perceive through retinal images, maybe retinal images or these brain stuff, etc., it is needed for our recognition, like you also said that. And we recognize objects through them, through this visual processing.
So Gibson doesn't have much to say about processing. It's just like, well, the visual system has sort of evolved to pick up on this type of information. The next, I've moved the reading for tomorrow up from the end of semester, this Hasson thing about direct fit to nature. And I guess that might offer a sort of account of how this pickup might work. But basically, like that from point to point, the information is best thought of as something like vectors. Yeah. And then the sort of the visual system is these sort of changes in the light from one point to another. Yeah. Now this is something that can be understood independently of any particular visual system. Yeah. Now, for example, that we only pick up on a small range of wavelengths. There are other animals that pick up on what broader things. So there are some animals that have less. So I think some animals don't have yellow. So I think, you know, for lions and tigers, for us, we see them out there and they're really obvious. They're not camouflaged at all. Yeah. But for their what do they eat? They eat these wildebeest or whatever it is. Wildebeest only have two cones, I think. So they see tigers as green. Yeah, the tiger and the grass just look the same color. Yeah. Now of course there is information in the light to in some sense differentiate the tiger from the grass. And at any particular point where there's a tiger and some grass behind it, there's information in the light that's sort of, you know, here's a yellow bit of light, here's a slightly greener bit of light. Now, for creatures, some creatures have evolved to be able to pick up on that difference, but other creatures haven't. Yeah, so it turns out that a lot of the prey of tigers haven't yet evolved to spot tigers in the grass. Yeah, that's why tigers haven't evolved to be green. Yeah, I think if you know, if you get these kind of lucky things that evolve, the wildebeest or whatever it is that get hunted, the antelope, if antelopes, you know, evolve the capacity to distinguish between, so there's the information available in the light. So at any point, yeah. So let's go back to this picture. What was it, page 62? Am I? So this is. Sorry, let me. Yes. Oh, wrong one. I've got too many things open. Oh no, am I sharing it? Yeah, here it is. Okay, so like for example, let's suppose this is green and this is tiger colored. Yep. So at this point here, we can kind of divide the pyramid at this point into kind of green and yellow. Now, of course, this is all going to be subdivided because there's going to be slightly different shades of green. There's going to be shadows. Each leaf is going to have a pyramid coming on it. So at this point of observation, that there's a kind of green, there's a yellow light and there's a green light. But of course, the only animals that have developed visual systems that distinguish between green and yellow light are going to be able to have a clear distinction between this and this. Yeah. Yeah. So for the antelope, if this is tiger colored and this is grass colored, then there's not going to be a strong division between here and there. There will be kind of lots of little patches, like all of these leaves will be different color. This is going to have a slightly different surface texture, but there is information at the light, and we can think of at any point, we've got these things coming out, we've got different intensities of light, we've got different hues of light. Yeah. But of course, the different animals have developed visual systems that are able to pick up on different aspects of the light at any particular point or in any particular pathway. Yeah. So in some sense, there's a way of describing this that is independent of any particular organism. Yeah. But then for any particular organism, there's only going to be, you know, the way you divide this up in terms of ways that's useful to understand how humans go about doing stuff is going to involve there's certain types of light that human beings are not sensitive to. So the sort of ultraviolet information, you can forget about that when understanding human vision. Yeah. But you might, if you want a general picture of what's available in the light, you might want all of that. And then the fact that there's information there in the ultraviolet light partially plays a role in partially explaining why some insects have evolved to develop the capacity to pick up on in ultraviolet light. Hesna.
What I was trying to tell is that you certainly did answer me, and for example, we somehow know that for example, green stuff can be eaten mostly. I mean, etc. But other organisms maybe do not see it in that way.
Yeah.
For example, omnivores, etc. It's kind of something developed afterward. So is it also possible?
Yeah. So
I
take it the sort of account he's offering in this paper and the sort of account of in the book, the color perception stuff isn't given a central role, because you need to be able to differentiate, have some way of picking up on different parts of the spectrum, because that's sort of what the information is. Yeah, but of course for us, colors play a really important role in categorization. Yeah. And so Gibson thinks that, and even not for us, like for bees, for example, the colors, you've got green backgrounds, you've got colored flowers, and the flowers have evolved to be colored to attract bees, and the bee's visual system has evolved to be able to pick up on flowers. Yeah. And so you had this co-evolution between the environment and the insects, such that certain colors have a certain meaning. It sort of means food. Now, Gibson in the book makes a distinction between categorization and perception. Yep. So, and I take it that the way in which colors, red means danger or food. I do think that what we're learning to categorize are going to be certain types of possibilities of action. So when the bee sees red, it sort of means pollen, maybe. Yeah, there's a possibility of collecting nectar. Yeah, but I take it the way in which color is used to categorize things is going to be something that's going to it's going to be something that's not so basic when it comes to the visual system of land animals. Yeah, the basic thing is about navigating an environment, I guess, like recognizing predators, but there's avoiding predators, And then there's also avoiding falling off paths. You may think that one good thing about vision is we're able to spot food in the distance, and then we're able to find a pathway to it. Now, I guess spotting food in a distance, it might just be that for animals that eat fruit, fruit have evolved to be colorful. And so, we look out for colorful things in the distance that don't move, because colorful things that move by themselves are often dangerous or poisonous, and then we try and find a path there. Now, how we go about spotting, recognizing something as fruit in the distance, that's something that Gibson doesn't address here. But I think the story might be quite simple. It might just be, oh, there's something, red means fruit. There are certain things that we now, and there you might think well, maybe there's some learning there, maybe there's some sort of associations of, maybe it's hardwired. Gibson doesn't say very much about that aspect of the visual system, at least in this article and in the book. He does have some things to say about color perception, but I think in some sense he thinks that's something that sort of comes later. The first thing about the visual system of land-based animals is that it's used to kind of navigate in a kind of cluttered environment. I think predator avoidance, you might think that's something that evolved very early on. I think the first kind of use of light information was just bacteria that move towards the light. So you have some very simple kind of anyway, next class I'll say a bit more about Gibson. It's quite difficult. This stuff is really quite difficult, and I just can't tell, doing it on Zoom, I can't tell how much of this, if I'm just talking nonsense for you, or whether it makes any sense. So I think in class, and also some of this stuff is much easier when you can move. You can illustrate in terms of movement. So tomorrow in class we'll talk about Gibson, and then we'll talk about this paper by Hasson about direct fit for nature. And he takes himself, or they take themselves to be taking some lessons from machine learning that might be used to support a kind of something like a kind of more Gibsonian position. Okay. Bye-bye. I've got to go because Zubaide's got to teach.